Today, we are going to talk about interconnect. This morning, a lot of people talk about the interconnection of renewable to existing grid. So today, I'm going to present the tool we developed in EFTP to automate that. So in terms of agenda, we are going to start by introduction. What is interconnect? Why do we need it? We are going to discuss the preparation of the IBR model because the interconnect tool is an automatic tool. So there's a small work of preparation on the model to be tested. We are going to see how to set up the tool and start analysis. We are going to see how to get analysis result. I'm going to insist on some features and we will conclude. As you know, the number of renewable generation units in modern power systems is increasing. This morning, we have a lot of presentation mentioning that. And as you know, before being interconnected to an existing grid, the behavior of any IBR plant should be validated through a series of tests. So there are some tests that are designed by the grid code that aim to check some requirements, to make sure the behavior of the IBR model complies with the requirements of the grid code. As I said, those requirements are defined by the transmission system operator. They are also referred to as the grid code. For instance, we have this IEEE standard, IEEE 2800, which is the standard for interconnection and interoperability of inverter-based resources. So these standards specify actually how to perform interconnection tests. What should be checked? How are the requirements verified actually? And in that document, we can summarize the test in three categories. We have initialization test because, as you know, when you deal with renewable, initialization is very, very important. My colleague, Professor Masrojan, insists on that during his presentation this morning. We have also step change tests. In these tests, actually, we apply step changes in reference on the IBR side. For instance, the reference of the power factor or the reactive power, the active power of the voltage, and we track the behavior of the IBR. So we track the response of the IBR, and the response could be quantified by like the reaction time, the step response time, the steady state error, whatever. We also have the high truth test. I don't need this actually.
I think it is better because
okay. So in that document, in that IEEE standard, there is also this category of test, right test. In this category of test, actually, we apply perturbation on the grid side, and we check that the IBR model remains connected to the grid for a minimum amount of time. That minimum amount of time is defined by the severity of the perturbation which is applied from the grid side. So, based on everything I just said, each test actually is performed in several operating modes called the configurations. So we have the test that should be performed, and to run each test, we have several configurations. The configurations are the settings of the IBR model. For instance, you may set the active power, the reference active power, to its rated value or to its minimum value. You may need to set maybe the reactive power to 0 or to its maximum value. Same for power factor and so on. So you understand that we can define several configurations to test the same IBR model. So when we have a test, we have the configurations. We may need to apply several scenarios. For instance, if we think of a test like the fault right test, we may need to try three-phase test, three-phase ungrounded fault test, single-phase fault test, phase-to-phase fault. So what I need you to understand here is that actually, there are a lot of tests under a lot of configuration and a lot of scenarios. So this requires to run a huge amount of simulations. And the way it is done now is manually. And you understand that it is tedious to do it manually. And when you do it manually, actually, you can make some errors. You waste a lot of time. You are not efficient. You are an engineer. You need to be efficient. And to be efficient, you need to automate. So actually, the interconnect tool is a tool that automates the execution of tests and concludes if the IBR model meets the requirement for interconnection to existing grid. So actually, we have a current version of the tool in EMTP Works. That version implements the prerequisite of the IEEE 2800 standards. We are currently working with some partners to develop, to integrate their requirements in the tool. So the tool can be easily adapted for any other grid because it's very flexible. We will discuss that later. So we can integrate different requirements from different grid code, and we can integrate different tests and different test definitions. So if we think of the interconnect tool as a black box, as an input, we have the model to be tested. and as an output, we have several outputs, but the main output is the report. It is an analysis report that presents the conclusions. For each test, the report tells if the test is okay or if the test is not okay. So if we want to go inside the black box, actually the interconnect tool create the simulation file, run the simulations, generate the waveforms, perform the calculation to check the requirements, and print the results in a report. So now we are going to talk about the preparation of the IBR model. Because as I said, as the interconnect tool is a fully automatic tool, there are some requirements. The model should meet some requirements to be able to be understood and interpreted by the tool. And these requirements are quite simple. Any model can be adapted. So actually in the IBR model,
in the center. The center is center.
It's okay. Okay, I was saying, yes. So there are some requirements for the model to be tested. Actually, it should be a black box. The model should be developed in EMTP works, of course. It should be a black box with one input bit, as you see, TREF, the input bundle bit that contains these signals. The signal for the variation, for the deviation of active power, reactive power, power factor, voltage. Also, in the mask of the device, we should have some parameter to identify the reference for active power, reactive power, and so on. So this, okay, yes. So in the model, you should have this, in the mask of the model, you should have some parameter that identify this quantity. The name, we don't care about the name because as we will see later in the tool, there is a step where you specify the name, you select the name of each, the name that represents each parameter. So after doing that, you simply save your model in an ECF file or a CLF or inside a library. If your model requires some additional files than DLL or whatever, you simply put them alongside inside the same folder and that's it. So this is for the preparation of the IBR model. So as you can understand, all models will be adapted to be able to be compatible with the tool. Okay, now we are going to move to the next topic, which is setting up the tool. So to set up the tool, we have to go through 6 steps, but actually there are only 2 mandatory steps, step 1 and step 2, because they are related to the characteristic of the grid at the point of interconnection and the characteristics of the IBR model to be tested. The 4 other steps are related to the grid code actually, and normally you are not supposed to touch unless you want to play with the tool and try some variants, some combinations, some different settings from the grid code. Okay, so when you launch the tool, actually this is what you see. Here is the EMTP works interface, this is the workspace. There is a window, there is something that appears, and this is the interconnect panel. So we have to go through the 6 steps. This is step 1, grid data. Here we define the characteristics of the grid at the point of interconnection. Here in the working space, we have typically, let's say, 2 devices. We have this, which represent the IBR model to be tested, and you have this, which represent the grid device. So in terms of grid, you have the option to select a Thevenin equivalent, which is the easiest way to represent a grid. We can also select a custom grid. So if you have your own black box device that represents your grid, you can import, you can load it here and use it as the grid device for your analysis. So this is for step 1. So we define the characteristics of the grid at the point of interconnections. In step 2, actually we define the IBR model. We have this button to import, to load the IBR model to be tested. And here you have to specify some information about the model. Here too, you have to tell the tool, okay, for the active power in my model, this is the name I use to represent the active power, and it is in megawatt, for instance. The same goes for all these other settings. So this is for step 2, and this is what the user should have to do. The user has to do manually. But for the other tests, he can leave it like this. Because here in step 3, for instance, step 3 is related to the configuration, but the configurations are defined by the grid code, so you can simply keep the default configurations. It's the grid code that dictates, okay, you have to do the test under this configuration. The active power should be set to this value, maybe rated value or minimum value, reactive power same. So these are defined by the grid code. So you may leave it like this. You don't have to touch it if you are testing a model following strictly the requirements of the grid code. And then we have step 4. In step 4, we define the test. here, by default, all the tests are selected, and each time a test is selected, you have to define the configurations under which the test will be performed. And if you follow the grid code, actually, this is already done. You simply need to keep the default value. But if you want to play, maybe disconnect some configuration, if you want to play and generate a customized report, whatever, you can do that. So this is for step 4. And then we have step 5, where we define some data used to create the secrets and evaluate the test. This is an example for the voltage write-through test. We have, for instance, if you want to do a voltage write-through test by applying fault, you need to define the type of fault. If you have 3-phase fault, you need to specify the impedance of the fault. So all these information are defined in this step. So we have sub-steps for each test. So for each test, we have some data we need to provide. But as I say once again, you don't have to understand this if you are following the grid code, because they already match, they correspond to what the grid code requires, actually. And of course, they could be customized based on your needs. So this is for the step 5. Now the last step, which is step 6, defines the analysis options. Here you have the option to run the simulations, and you can run the simulation one by one sequentially or run in parallel. There is another toolbox to do that. So if you want the computation time to be faster, you can run in parallel. You can click this button to generate report, and here you can decide how many reports you want to generate. Actually, you can even decide what to put in the report. And this is also an interesting feature. Maybe I will come back to it later. So you can define the number of reports and the content of each report. Here we have other options. I will talk about that briefly in a moment. So this is how we set up the tool for E-interconnect analysis. So as I said, step 1 and step 2, they are the mandatory steps that are set manually. The other step, you can keep the default value. So after setting up the tool, you can launch analysis. And after analysis, the tool generates some results. And in terms of results, actually, we have a folder which is created that will contain all the simulated ECF files. So if your analysis requires maybe 100 simulations, all the simulation files will be generated inside this folder. There is this other folder that contains the report. It's a Word report. If you have one report, you will have only one file here. So this is simply an error. If any error occurs during your analysis, you will have the description of the error here. And this is also simply a log file that lists. If you want to understand each action that the tool did, actually, they are summarized here inside this report. So this is an example of report. So when the process is completed, you have a report like this that starts by a description of the grid, description of the IBR model tested, a table of content, a description of the test, the configuration, and finally you have this executive summary that quickly tells you which test was okay and which test was not okay. After this executive summary, you have the detail for each test. For instance, for the flat start test, you have this. This is how it looks. I took screenshots. So there's a table that lists the parameters used to create the secrets for flat start test. Here I can say a word. For instance, here you say that for the flat start test, we have three parameters that define the test. This parameter T start is when you begin to observe the signal. T delay is for how long you observe the signal. The margin here, for the flat start, the signal should be flat. But when we say flat, what do we mean? What we mean the signal should not vary more than 5%, for instance. So this is how we define the flat start. And in the report, you have the screenshot of the active and reactive power, because this is the quantities we track. And then you have this sentence that tells you if the power after initialization is constant or not. And you have the conclusion for this test. This is for the flat start. For another test, the content of the report is different. For the reactive power control test, for instance, you have the parameters that define the test here. Here, we plot in the report the reference and simulated reactive power. And here you have a table that tracks actually the behavior. If you evaluate, for instance, the step change number 3, which is this one, yes, you have in this table a value of the reaction time, the value measured in the simulation, the reference value from the grid code, and then the conclusion. So when a test failed, you know exactly why the test failed, which is the parameter that failed actually. So you have this, and the same goes for all the tests. I don't have time to go through all tests. So this is how it works. So now to conclude, I'm going to present to you some features of the E-interconnect tool. The E-interconnect tool is very, very, very flexible. It is possible, as I presented earlier, to to use a custom grid device. It is possible to customize the report. As I said, you can decide how many reports you want to generate. You can decide the content of each report. And this is particularly interesting if you are working on a project. You have a Word document, you have started writing on the document. You want to use the tool to generate some figures and populate your report. So it's possible to say, okay, in my Word document, go to this location and put the result of maybe the reactive power for test number 3. I said there's a way to tell to set up a Word file in order to so that the tool can print the relevant information inside the file. So this is a good element of flexibility. Also, with the tool, you can do waveforms comparison. So if for a given quantity you have some reference data coming from the field or whatever, and you want to compare with the results of the simulation, you can do that. Also, if you receive several versions of the model, for instance, you receive a model and then 3 months later you receive another version of the model, you run the new version and you want to compare to the results from the previous version, you can do that. Yes. Also, if, as I said, you know, the interconnect tool, when it runs, it takes time. It may take more than 1 hour because it generates a lot of ECF files. And during the process, maybe something may happen. Maybe your computer may crash, or I don't know, maybe your computer may run out of power. I don't know. Imagine you are running 100 simulation at simulation 25, something happens. So in the tool, when you restart, the tool is able to know that, okay, I can restart your aborted analysis. I know that previously I stopped at simulation number 25, and I will simply continue from there. So everything that has been simulated is not lost if something happens to your computer. Also, you can plot figure after analysis because the way it works, the figures are printed to the report. But if you want to plot a figure to zoom or to observe something special, you have access to the ECF file. You can go and generate the figure yourself. But in the tool, there is a way to quickly access the figures presented in the report. So these are some features that are quite kind of interesting. And as I said, the tool is very flexible. It can be adapted for any grid code, actually. A transmission system operator, which is already doing integration studies, may decide to use the tool to automate. The tool can adapt to its way of doing the analysis. So you can follow what you say in the tool, but we can also adapt the tool to match the way you already do your test actually. So with that being said, I think that concludes my presentation. So I'm going to una pregunta.